Convection and weather, two pretty important concepts in this course. So, what happens is this: light from the sun is a form of energy, and energy can never be created or destroyed. This is called the first law of thermodynamics. So, what happens is sunlight that doesn't get absorbed by the upper atmosphere, by the ionosphere or the stratosphere, when it hits the ground, some of it will bounce off back into space. It's called albedo, but a lot of it will be absorbed by the ground. And when it gets absorbed by the ground, it has to take another form. You can't destroy that energy, it just has to take a different form. And the form it takes is thermal energy, which we sometimes call heat. So what happens is sunlight delivers energy to the ground, causing the ground to gain heat. Now, what happens is the ground then transfers that heat energy to the air immediately next to it in a process called conduction. So conduction is just the flow of heat from where it's warmer to where it's colder. So the air that's immediately next to the ground gets hot. Well, what happens to hot things? Well, they expand because when things are cold, the atoms can be close together, which lets them have high density, and things that have high density sink. What happens is when things hit each other with more and more violence, they get farther apart. They're just farther apart, and that makes them less dense. So things that are less dense float upwards. So the air near the ground, being hotter and less dense, is going to begin to float upwards. And this is a phenomenon that is known as convection. So hot air that's near the ground becomes hot. Hot air rises because it's less dense. Now, as it moves up, if you remember our diagram of the troposphere from the other presentation, the temperature steadily declines as you go up. And so what happens is, as this air goes up, it loses temperature and becomes colder. Now, it moves up so fast, it overshoots where it should be, overcools, and then it falls back to the ground, and the process keeps going. So any place we have uneven heating, one area of the ground that's warmer than another one, we're going to get convection. It doesn't necessarily have to be hot. I mean, this happens in the Arctic. It happens over the ice caps. I mean, if you just have one part of the ground that's warmer than the other parts around it, you're going to get rising air in that one area, and that's going to cause convection. Now, this circular pattern that we get, we call a convection cell. All right, and so basically, it's all predicated on solar radiation causes the ground to get hot. Conduction between the atoms in the ground and the atoms of the air, heat them up, they become less dense. The ones that come left, they move upwards. Now, latent heat release is something we'll talk about in a minute. But for right now, let's just worry about this circular movement that we get. It's called a convection cell. So as long as there is an area that is warm, we're going to get this circular pattern of wind around it. And this actually happens in 3 dimensions. So we call this a convection cell. Now, here's a good classic example of it. It's called the sea breeze and land breeze. So here's what we find. So during the day, let's say the sun shines down. Well, the ground is going to be warmer than the sea. Now, this is true in the wintertime. It doesn't have to be hot. It's just that this is going to be warmer than this. So what happens is, since the air is hotter here, it rises up. Since it's colder here, it sinks down here. So we get this pattern of air movement here. All right. Now, what happens is, if I was here, let's say on this boat or standing here, look at which direction the wind is blowing. That's because all wind is the movement of air from one place to another place, from where it's rising, from where it's sinking towards where it's rising. That is all the wind is. Anytime you feel the wind, it's because air is rising in one part of the planet and it's sinking on another part and it has to move between those two places. That's wind. Look what happens at night. The sun goes down. Now the water is warmer than the land because it's harder for water to cool down, but it's easy for land to cool down. So now what happens is, since this is warmer than this, the air begins to rise here and sink here. And notice the wind is now blowing the opposite way because it's always going to blow from where it's sinking towards where it's rising. Now let's talk about this latent heat. So here's the deal. As air moves upwards, it gets colder. And as it gets colder, what happens is rising air carries with it water molecules. Now, as they move up, the air gets colder. The air carrying those water molecules gets colder. This adiabatic cooling it depends on the moisture content of the air, but it's about 7 degrees for every kilometer up that we go. So you go up if you start off at, say, 20 degrees at the surface, you go a kilometer up, it's likely to be about 13 degrees. You go another kilometer up, it's likely to be about 7, how was that, 6 degrees, okay? And so on. Well, it turns out that the water content that can be held by air depends on temperature. So what we find is this, and there's one idea today I need you to get your head around. It is this. You've got to get this one. It's crucial. Rising air is going to produce clouds and rain. And the reason is this. As air rises, it carries evaporated and transpirated water molecules with it. It's in a vapor state, a gas. As convection carries it upwards, adiabatic cooling drops the temperature about 7 degrees for every kilometer. At some point, the temperature is going to get so cold the water cannot stay as a vapor anymore, and it starts to stick in a process we talked about earlier in the year called condensation. It condenses because it's colder now. Now, as that happens, it's going to release energy. If you remember from chemistry, we talk about the heat of vaporization. It takes a lot of energy to separate water. That's why you had to boil water. You had to put a lot of energy into water to make it boil. Well, same thing about evaporate. It takes the same amount of energy to make it evaporate as it does to boil. It takes 580 calories to make 1 gram of water become a vapor. But when 1 gram of vapor comes back into being a liquid, it's going to release that same amount of energy. I know in calories, so 580 calories, multiply that by 4, and you've got basically joules. The point is, when clouds form, they release a lot of heat energy, and that heat energy further pushes the air upwards. But the main takeaway here, the main thing I need you to get into your head is that rising air is going to result in clouds and precipitation, because as that moist air goes up, it's going to cool off, condense, and precipitate. Please don't forget that. Now, another thing that's worth noting is what happens to pressure. Here's just another example of this before we talk about pressure. So the idea is this. If the air is rising here, then what's going to happen is we're going to cause precipitation and condensation and precipitation here, because rising air is going to cool down and lose the ability to keep water in a vapor state. But the sinking air is going to be dry. We don't associate precipitation with sinking air because it loses moisture on the way up. Now it doesn't have that moisture when it comes back down. Now, what happens is what this will do over the course of the day is it will keep picking up water molecules off the ocean, carrying them over here, and then precipitating them over the land, the water cycle. But this air is now, it's like a conveyor belt that's dropped off its package. It doesn't have any water, has very little water molecules left in it. So sinking air we associate with clear skies and dry air. Now the night comes. What happens is the air goes the other way. Now we have warm air coming up this way. So anytime the air is rising, that's where we expect to find clouds and precipitation. Where the air sinks, we expect to find dry air and clear skies. Now, the troposphere is basically where all the world's moisture is contained. So what we find is that convection is confined to this area here. When I heat the surface with the sun, I can't get convection to go any higher than about 10 kilometers. So the top of the troposphere is pretty much the limit to which we can carry water vapor up through convection by heating the Earth's surface. Now let's talk about pressure. Okay, so I thought this was going to be earlier in the presentation. Now, some students have a hard time with this idea. We're only going to concern ourselves with pressure on the ground. We're not going to worry about pressure as we go up. We've already talked about how pressure changes with height. But let's just talk about on the ground. If I heat the area here, the atoms get farther apart, and convection causes the air molecules that are here to move this way. That means there's fewer atoms here. Less atoms means less pressure. Think about this. I have a tire. I let air out of the tire. If there's fewer molecules in the tire, what happens to its pressure? It goes down. All right. If I pump air into the tire, what happens to the pressure? It goes up. So taking atoms out of an area makes the pressure drop. Adding atoms into an area makes the pressure go up. So look here. Low pressure carries atoms away from this area, so rising air is associated with low pressure. Now, as this air goes across here, it sinks back down. Now, I'm adding air molecules to this area. It's like pumping air into a tire. As I add air to here, the pressure is going to go up, so I'm going to have high pressure. Sinking air is associated with high pressure. Rising air is associated with low pressure. All fluids will move from areas of high pressure to areas of low pressure. So it gets pushed this way. Now, so the takeaway then is rising air is associated with low pressure and precipitation. Sinking air is associated with high pressure and clear skies because this doesn't have any water. It lost it on the way up. All right. Now, thunderclouds are kind of interesting. So when you see a thundercloud like this that has an anvil on it, this is basically 10 kilometers up. This is the top. You can basically see the top of the troposphere in these clouds, which is pretty remarkable. Now, airplanes can only fly about this high. So you'll notice airplanes try not to fly through thunderstorms. It's not because they're afraid of getting hit by lightning. They just don't want to be caught in the powerful convection currents that are present in these tall thunderstorms. Now, one of the things you expect to know in APES is the idea of what's called a rain shadow. So what happens is sometimes we have prevailing winds. We'll talk about those in a future presentation. But in areas on the planet where the winds blow in a particular direction, on a normal basis, if winds are moving off of the ocean, they're going to be carrying a lot of moisture. Now, as they carry that moisture inland, if those winds that are going a certain direction hit a mountain, that mountain is going to launch them like a person on a motorcycle going off a ramp. They're going to send the air upwards. As that air moves upwards, remember, if you move upwards, the temperature goes down, and then anytime air is moving upwards, it is going to precipitate. So no matter what, whether it's convection or if it's air that's being forced up by hitting a mountainside and being knocked upwards, rising air causes precipitation because it gets colder. So what we find is a really fascinating thing. When there's prevailing wind directions, we often see this pattern. It's called a rain shadow. Moist air coming off the ocean, and it doesn't even have to be warm. Moist air coming off the ocean hits this land. So the wind is blowing this way. As it hits the mountain and it moves upwards, as it goes upwards, it gets colder and colder and colder. And then what happens is you reach a certain level where cloud forms and all the moisture in it comes out as precipitation. So now the air, by the time it gets to here, it's already lost all of its moisture. So the air the air is very moist, but it lost it moving up the mountainside because it cooled down and condensed. So the air that comes back down is now dry. And as it comes down lower and lower, it warms up and it can absorb more and more water from the ground. So what we find is the air here, it just is super dry. It's like a desert. So what you can find is places on the planet, including the state I come from, Washington State, where there'll be mountain ranges. One side of them will have rainforests, and the other side will have deserts. I mean, it's amazing. Where I come from, you can literally get in a car, and you can go from one side of Snoqualmie Pass, where you are literally in a temperate rainforest, and 15 minutes later, you are literally in a desert. And the reason is because you've moved into a rain shadow. The winds are coming out of the west. As they move up the Cascade Mountains, they go higher and higher and higher. They get colder and colder and colder. The moisture they're carrying condenses and precipitates on the windward side. And as it comes down the leeward side, as we call it, it's dry air. And that dry air, as it descends, warms up. Just as rising air gets colder, sinking air warms up. Warm air can hold more moisture. So whatever moisture is here ends up going into the air, making it even drier. So this phenomenon is called a rain shadow. And here is a rain shadow from the northwest where I come from. So this is the Cascade Mountain Range. And what happens is, as the air comes in here from the Pacific Ocean, it rises up these mountains. As it gets up to here, it precipitates because it's being launched upwards. And as it comes down the other side, it no longer has any moisture in it, and it sucks up what little moisture is there, and we get this desert in the side of Oregon over here on the other side of this mountain chain. All right, so that's rain shadows for you. Thanks for watching.